In the last episode of our show, we talked all about black holes. We talked about what it would be like to fall into a black hole, how time passes differently as you approach a black hole, and even the weirdness of how time and space seem to switch roles when you cross the event horizon and approach the singularity at the center of a black hole. So we kind of established that black holes are weird in that episode, but it turns out that we actually missed a lot of the weirdness of black holes because in that episode, we completely ignored the effects of quantum mechanics. We tend to think of quantum mechanics and general relativity as these two completely different and very incompatible theories of our universe. But black holes are one of the few places in nature where we see them working right next to each other.
Yeah, other than like the Big Bang itself, probably the only place in our universe where the effects of general relativity and the effects of quantum mechanics are both like fully manifest are in black holes. It turns out that when you combine the already weird stuff about general relativity with the equally weird stuff about quantum mechanics or quantum physics, black holes turn out to be maybe more bizarre than anyone has any right to expect.
So stick around to find out what happens when we take our study of black holes and ask, what does quantum mechanics say about this? You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. So if you just take the equations from Einstein's theory, general relativity, and see what black holes should be like, it turns out they're pretty simple. The solution to these equations for a black hole can be described entirely in terms of exactly three quantities. If you know the mass of a given black hole, you know how fast it's spinning, and you know how much electric charge it has, you've entirely described the black hole to every level of precision. That's all you need to know to perfectly describe the black hole according to those equations of general relativity.
Right. So like according to those equations, if you had two black holes with the same mass and spinning in the same way and with the same charge, they would be totally identical to each other.
Absolutely. Totally identical. The phrase that physicists use to kind of express this is to say that black holes have no hair. Two black holes with the same mass, angular momentum, and charge are truly the same object. They're totally indistinguishable.
Does that mean like your hairstyle is what differentiates you?
Well, I think the idea is if you focused in on the surface of my arm or something, you would see a bunch of like small, fine resolution details like hair. And black holes don't have any of that. According to Einstein's theory, anyway, they don't have any hair.
Okay, so very smooth.
Yeah, they have no small structure, no detail, no fine structure at all. So this was an idea put forth by John Wheeler in the 1960s. So John Wheeler was one of these really brilliant physicists of the era who did a lot of work on general relativity. But perhaps his greatest accomplishment is producing a huge string of really successful PhD students under his supervision. In this podcast, we've already talked about several of his students, like Richard Feynman, Kip Thorne, Hugh Everett. All of these were Wheeler's students in this era. And today we're going to talk about two of his other students, Bill Unruh and Jacob Bekenstein.
Was it just luck or was he just a great mentor?
I don't know. He must have been good at it. I don't know. So if Wheeler was right and black holes really have no hair, this runs into some problems with the second law of thermodynamics. So if you remember from our episode on the arrow of time, we described the second law of thermodynamics, which basically says the entropy of any closed system is always going to increase or always tends to increase. And you can think about that entropy in terms of information if you want. You can't ever erase information from a system. You can make more information in certain physical ways, and you can conserve it, but you can't ever take something that had information encoded in it and rearrange it in a way that has less information. That just can't happen according to the laws of thermodynamics.
So, like, for example, if you throw a dictionary in a fire, theoretically, all of the information about all of the words and definitions are preserved in the ashes in some way.
If you could, measure precisely every little atom and molecule and all their velocities and the form of the heat and the ashes and the light and all this stuff, you could reverse the laws of physics, run them backwards and reconstruct that dictionary in all of its detail. Now, of course, in practice, no one can do this, but the laws of physics say that in principle, you should be able to do something like that. You can't erase that information from the universe. But let's say you have a black hole, and I take that dictionary and I drop it and let it fall into the black hole. Once it's past the event horizon, now the black hole is just the same as it was, except now it's just, one dictionary worth of energy more massive, not very much. And if those three numbers, its mass, angular momentum, and charge, describe the black hole perfectly, its information content did not increase.
In other words, no information about the dictionary appears to be conserved because you can describe the entire black hole and its contents, including the dictionary, in terms of those same three numbers as before: its mass, its charge, and its angular momentum.
In other words, black holes seem to have no entropy and seem to contain almost no information. So where did all that information in the dictionary go? And if you want to think about it in terms of entropy instead, the universe had a certain amount of entropy beforehand. You drop something with entropy into the black hole, causing that entropy to disappear. So it seems like the entropy of the universe just went down in violation of the sacred second law of thermodynamics. So there's something weird going on here. And I think in the late 60s, no one even had a clue what the answer might be. So one of John Wheeler's students was thinking about this problem around this time. His name was Jacob Bekenstein. And this was the early 70s. And he calculated how much the mass of a black hole would change when you deposited into that black hole a certain amount of entropy, or equivalently a certain amount of information, a number of bits of information. And he showed that you could kind of go back and forth between the change of the mass of a black hole and the change of its entropy. All right, so for example, consider a black hole with a mass equal to the mass of the sun. And we're going to have one photon, one quantum of light, fall into that black hole. And we're going to pick that photon to have a wavelength, the maximum wavelength that can fit inside that black hole. So its wavelength is going to be equal to the Schwarzschild radius of the black hole. It turns out that photon carries exactly 1 bit of information. So the smallest amount of information you can get into that black hole. When that photon goes into the black hole gets just very slightly heavier, and that means it gets slightly bigger. The size of its horizon increases.
Why does it get heavier if photons are massless?
Equals mc squared, Shalma. So take a small amount of energy. It turns out that is equivalent to mass. So Einstein tells us that all mass really is energy without motion. So when this black hole's horizon grows a little bit, it turns out the area of the surface area of that event horizon grows, and it grows by a very small amount, but a very specific small amount, equal to 1 square Planck length. So the Planck length isn't just some number. It is thought to be the length scale at which the effects of quantum gravity really become important, where the quantum nature of space and time really become apparent.
So to understand this next bit, I'm going to pull something out of the world that physicists live in for a second and explain it. So you'll often hear physicists talk about lengths, energies, and timescales as if these three are all completely interchangeable concepts. This is pretty unintuitive. I mean, a meter seems nothing like a minute, and neither of those seems like a joule of energy coming from your light bulb. But by using two very important fundamental constants in physics, time, length, and energy seem to become just different sides of the same coin. So there's two of these constants. The first is the speed of light. So we know that everywhere in the universe, the speed of light is the same number, it's constant. And speed is just how far you travel in some amount of time. So you could see the speed of light as just a natural proportionality factor between lengths and times, right? Speed being length over time. So that's the first constant, and the second is something called Planck's constant. This number is very relevant in quantum mechanics, and it relates the energy of a photon or particle of light to its wavelength. So its wavelength is just a length, and so this number is a proportionality between length and energy. So with these two constants, the speed of light and Planck's constant, we have a way to interchange between any length scale, time scale, or energy scale just by multiplying by the appropriate proportionality factors. Okay, so this might be pretty out there, but with this in mind, let's go back to talking about the Planck length, which you now know is equivalent to talking about a Planck energy or time length.
So you can think about it this way. If there were a photon that had a wavelength equal to the Planck length, so this would be an enormously energetic photon, like wildly more energy than anything we can build at particle accelerators or something, that photon would contain so much energy that if it got in the proximity of anything else, it would instantly form a black hole. So you can't talk about particles with that much energy without talking about general relativity at the same time. So basically, we don't know what the theory is that works at those scales, but some sort of quantum gravity theory has to work there. So this is the length scale or the energy scale or the time scale, whatever you want to think of, where all this stuff goes haywire. So what Bekenstein's calculation showed is that when entropy or information goes into a black hole, its area increases in this very predictable fashion. When that tells us the area of a black hole, the area of the horizon of a black hole is directly related to how much entropy it contains. And it turns out, according to this calculation, that black holes contain a lot of entropy. In fact, Bekenstein showed that a given black hole contains more entropy than any other form of matter could contain in the same region of space. Furthermore, the entropy of a black hole, because it's proportional to its area and not its volume, there's something really weird going on here. I mean, if I wanted to know how much entropy a cup of water had, it would be proportional to how much volume of water I have. But a black hole is different. Somehow the amount of information it has doesn't depend on the volume of space it occupies, but the area of the surface enclosing that volume of space. So something really bizarre is going on here.
So this behavior is kind of akin to something like a hologram, an object that appears three-dimensional, but it's actually just a projection from a two-dimensional amount of information or a 2D screen. So we'll talk more about this idea later in the episode, but first let's get some more of the story.
All right, so all this is going on at Princeton with people like John Wheeler and Jacob Bekenstein, but across the pond in England at Cambridge, Stephen Hawking is thinking about some similar ideas. So when he first heard about these ideas of Bekenstein's, I don't think he found them very persuasive, or at least briefly thought that way. But eventually he would kind of get on the same train and build upon Bekenstein's ideas and see where they would really take him.
Do you know why he didn't find them persuasive?
Well, in 1970, he had postulated kind of the opposite thing. And I think he was pretty loyal to his own idea, like lots of physicists are.
Lots of everyone, yeah.
Yeah, lots of everyone. Physicists especially, maybe. He postulated this thing he called the second law of black hole dynamics. Is kind of an analogy to the second law of thermodynamics. And this law that he postulated said that a black hole's horizon could never get smaller. Okay, it'd only get bigger or stay the same size. So kind of like entropy in thermodynamics. So it's kind of ironic, but Hawking's analogy was maybe closer to reality than he had realized. If he had taken the analogy with thermodynamics more literally, he might have actually been led to the right answer more quickly. But anyway, that's an aside. So Hawking was influenced by Bekenstein's work, but also by the work of some theoretical physicists in the Soviet Union, like Yakov Zeldovich, Starobinsky, these great minds of Soviet theoretical physics. And they had shown, or at least argued, that specifically rotating black holes should radiate particles. And if they were radiating particles, and they would lose energy and therefore mass, causing their horizons to get smaller, in contrast or conflicting with Hawking's second law of black hole dynamics. What Hawking then recognized is, if you put all this together, was that if black holes really had entropy, contained information, the way that Bekenstein had shown that they probably did, then they would also have a temperature. And things with temperatures radiate light, among other kinds of particles, kind of like Starobinsky and Zeldovich had been showing, at least for the case of rotating black holes. So from this perspective, no black holes should really be all the way black. Black holes themselves should be radiating light, although not very much of it. And we now call this light and other forms of particles radiated from a black hole Hawking radiation. All right, so there's a big question all this raises about what's actually going on. Like, what makes a black hole radiate particles? Like, so far it's about as opaque as mud trying to understand all of this. And it's not super easy to understand. I will concede that point. But what's really going on here is the complicated interplay between weird general relativity stuff and weird quantum physics stuff kind of going on at the same time. So there's a related thing which will help us get to the right answer called the Unruh effect, which was worked out in the 70s by a few different people, Stephen Fulling, Paul Davies, Bill Unruh himself. And basically they were imagining what things would look like to an observer who was accelerating really, really fast. To this observer, there are regions of space behind them that light can never reach them from. Even traveling at the speed of light, the fastest possible speed, that light will never reach them if they're accelerating at a great enough rate. So you can think of there being a horizon behind them, kind of like a black hole horizon, which causally disconnects the space ahead of them from the space behind them. But quantum mechanics says that those regions of space ahead of them and those regions of space behind them are entangled or not independent in a quantum mechanical sense of each other. And when you work out where that leads you, it turns out that accelerating observer should see particles kind of spontaneously being emitted all around them. From this perspective, quantum mechanics shows that empty space really isn't all that empty or simple. Instead, like in the accelerating frame, space itself emits particles into space, although just very slightly. Even if you were accelerated to 1 trillion times the gravitational acceleration on Earth, you would find this radiation is being emitted at like 40 nanokelvin, like really, really faint radiation of particles in all directions. So Hawking took this further, and he said, imagine you go up right to the edge of a black hole, to the horizon of a black hole. And then you use this equation I just described for the Unruh effect. And you can work out what the temperature of the resulting radiation from the black hole's surface should be from its horizon. And when you do, Hawking showed that all black holes will radiate a thermal population of particles, as if it had a temperature, with a temperature inversely proportional to its mass. So the biggest black holes will be the coldest, and the smallest black holes will be the hottest.
So this kind of radiation that comes from black holes is relatively cold, and the black holes that we can study are pretty far away from us. So we haven't actually observed any of this Hawking radiation yet, but there is definitely agreement among physicists that this probably exists.
So if you've heard about Hawking radiation before in other books or podcasts, or even on this podcast, there's kind of a cartoon picture of it that you may have been presented with. The idea is that right around the horizon of a black hole, the laws of quantum mechanics say that particles can just spontaneously come into existence. But when they do, they come along with an antiparticle. So like if you make an electron, you make a positron alongside with it. And sometimes one of these particles will escape, traveling away from the black hole while the other one falls back in. The particles that escape make up the Hawking evaporation or the Hawking radiation. And because that radiation is coming out, it makes the black hole slowly get smaller. So that's the basic picture that this cartoon describes. But what I want to drive home here is there's more to it than that, really. The whole surface of the black hole's horizon is filled with all of these tiny Planck length-sized patches which contain information, and all of those are entangled through quantum mechanics with each other. And that, combined with general relativity and quantum physics and all this, is what leads to Hawking evaporation. So that cartoon picture is like a good way to think about it. It was probably deep down isn't the whole story.
In the beginning of the episode, we talked about this no-hair theorem that comes out of general relativity. But now we know that because of these quantum effects, black holes actually do have entropy and do give off this Hawking radiation. So it turns out that black holes actually really do have hair.
They should have a lot of hair. They should be hairy black holes, the hairiest things in the universe.
Okay, so what's this black hole hair like?
Well, the short answer is we don't really know. Whatever the answer is, it almost certainly requires a theory of quantum gravity for us to really understand, and we don't have one of those yet. String theory is probably our most promising candidate for quantum gravity, and it offers us some, at least plausible insights into what the black hole hair or entropy is all about. And I'd say in more general terms, the elements we understand right now make us think that, based on the calculations of Bekenstein and Hawking and others, that the horizon of a given black hole consists of all these Planck-length-sized patches of space that are each entangled through quantum mechanics in this complex way. What that looks like and, how the information is stored and what stuff is there doing the storing of the information, I think is still just a mystery. We just don't know the answers to those sorts of questions. And it might be that next year we solve that and have a new theory, and it might be another 100 or 200 or 1,000 years pass, and we still wonder.
So is this a theoretical question, or is there a way for us to also experimentally observe properties of black holes that can help us answer this?
I'm confident that if we had a black hole that we could get up close to, and we could measure its Hawking radiation, we could measure, all sorts of things about the curvature of its space and time in its vicinity and all that stuff, we could at least, steadily get closer to answers to these questions. That being said, we don't have any black holes in our backyard, and I don't think we're going to detect Hawking evaporation anytime particularly soon, probably anyway. So it might, at this point, it is really a theoretical endeavor, but today's theoretical endeavor is the future's experimental playground.
So now let's return to one of the very odd things about black holes that we glossed over a bit. This idea that all of the information contained in a black hole is really just contained on its surface, like a hologram.
It sure seems like the horizon of a black hole occupies a 3D region of space. It encloses a 3D region of space. But their information content is proportional to its 2D, two-dimensional surface area. And it's led some people to say that maybe the black hole's information content, its entropy, is actually stored on its surface, not in its volume. An open question is whether or not this information that's stored in a black hole is carried out by Hawking radiation when that leaves the black hole. So if I drop that dictionary into the black hole and I collect all of the particles being radiated by that black hole, when the black hole is gone some very long time from now, would I be able to reconstruct that dictionary by somehow studying all those particles that came out of it? I don't think anyone knows the answer to this yet, but the answer to this question really tells us whether black holes can destroy or erase information or not. And this is, if they can destroy information, it means they're totally unlike anything else in physics. And if they can't destroy information, then we have a good reason to think that the conservation of information is like a real deep principle that pervades everything in our universe. This stuff is all related to something that physicists call the holographic principle. This is an idea that goes back to the late 70s. Great physicists Gerard 't Hooft and Lenny Susskind worked it out. And in the context of string theory, which they were working in, they showed that all the stuff that's contained in a volume of space, the information describing that stuff, could be encoded on the surface of that region of space. So if that's true, and I think a lot of physicists think it is, then maybe from the perspective of information, which a lot of physicists would argue is the real foundational stuff that makes up our universe might not be four-dimensional in terms of space and time, but only three, which is a pretty weird idea.
Mm-hmm. So the idea is, since all of the information in our apparently 3D or 4D, if you're including time, universe could be encoded on a two-dimensional space, that maybe that's what's actually real.
Yeah, I mean, in that sense, our, the three spatial dimensions that we know and love would be something like an illusion or a projection, much in the same way that a hologram, can be encoded on a 2D surface but make a 3D image. More recently, like some kind of fresh light has been shined on these questions from something called the ADS-CFT correspondence. So it's a bunch of letters. ADS stands for anti-de Sitter, which is a kind of space-time, and CFT stands for conformal field theory, which is a kind of quantum field theory. So this was proposed in 1997 by Juan Maldacena, and later kind of built on or elaborated on by Stephen Gubser, Igor Klebanov, Ed Witten, and a bunch of others. And in a nutshell, what it says is this. There are certain theories that describe a space-time within dimensions, and just being an integer. And you can show that those theories are exactly the same thing as certain other quantum field theories or particle physics theories in n-1 dimensions. So there's this one class of theories that are n-dimensional, and another class of theories that are n-1 dimensional, one fewer dimension. And you can show in certain cases that those theories are describing exactly the same stuff. So from the perspective of this holographic principle or the ADS-CFT correspondence, a lot of physicists in modern times are thinking that maybe things like the very number of dimensions that our universe has, or our conception of space and time itself, is maybe not as well defined or simple as we might have long thought it was. The answer to the question of how many dimensions of space our universe has might have more than one answer depending on how you think about it.
It's like the more we learn, the less we know kind of situation.
Yeah, I mean, I still think we're learning things about the universe that we didn't used to know, but we're finding out the stuff that we had used to once took for granted, maybe doesn't hold up to scrutiny all the way down.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jay Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.